Yeah, I forgot that you have the Zoom link, so that is only for the committee.
Oh, okay.
Okay, he will send it right away.
Thank you.
So I was sent the link by email, Yahoo, so you can directly in
Thank you.
YouTube.
Okay, thank you.
So voy a estar, las primeras palabras las voy a decir un poco en español y después vamos a pasar a inglés. Pero entonces les recuerdo que va a ser hoy día la defensa oficial de Víctor Ignacio Fernández González. Entonces les recuerdo que tiene ciertas formalidades y protocolos esta defensa. Entonces, en particular, Víctor va a hablar 45 minutos, no puede exceder ese tiempo. Posterior a eso, el comité, que está formado por distintos profesores, en particular está formado por el profesor Kiju de la Universidad de Softec Tecnología de Shenzhen, por el profesor Emiliano, siempre digo Emiliano Cortés de la Universidad de Múnich, también por el profesor, por la profesora Paulina Hidalgo de la Universidad de Concepción, y por el profesor Luis Foa de la Universidad de Chile, y por yo, en mi caso, soy yo el chairman, digamos, por mí como director de tesis. Entonces, Víctor tendrá 45 minutos para defender. Posterior a eso, tendrá preguntas del comité y posterior, el público tiene derecho a hacer preguntas siempre y cuando el público tenga un grado equivalente al que opta Víctor, que es magíster o doctorado. Entonces, aquellas personas que no tienen derecho a preguntar. Y posteriormente vamos a deliberar. Se me olvidó mencionarles, no se puede aplaudir al final de su presentación porque está siendo evaluado y solo puede ser, digamos, finalmente cuando el comité delibere, digamos, la decisión. Entonces en ese caso vamos a poder felicitar a Víctor en el caso que corresponda. ¿Está bien? Muy bien, Víctor. So we start. So we have 45 minutes for Víctor, and I was explaining the rules in Spanish, huh? Okay, so Víctor, you can start.
Okay, so thanks, Professor Marcel, for the introduction. Hello, everyone. My name is Víctor Fernández. Today, I will present my thesis dissertation, which is called Localized Topological Defects, Transitions, and Self-Organization. So, first to start, let me give a little outline. First, I will introduce some key concepts of the materials that I will talk, mainly liquid crystals and some things about nonlinear dynamics. Then I will go into talk a little bit of two chapters. The first one being the transition of topological states between disorder patterns, where I will explain a little bit of how these locations will emerge in disorder systems. And second, we are going to be talking about the aggregates of clusters that can emerge in chiral liquid crystal droplets. So we are going to be studying the self-organization that can occur in localized vortices inside this droplet. So let's start with some motivation. First of all, patterns are a general phenomena that we can observe around us. So they are ubiquitous, as we call, and we can observe them at different scales. For example, we can see them in animal spore. We can see them in the beehives that bees can create. We see in vegetation patterns in the sand dunes in the north of Chile, for example, and also in fish scales, which is another very beautiful example, as we can see patterns all around us, as I just said. So first of all, the thing that can be already obtained from these images is that nature tries to organize itself, creating these patterns, and now we want to study them. Nevertheless, we need some platforms so we can study them, and what we're going to ask ourselves is if we can study them on a lab. So we do have an answer for this, and throughout this presentation, I will be talking about the texture that can emerge in chiral nematic liquid crystals. So for example, here in the top row, you can see some experiments that we are doing and working in the lab, where I'm showing some different textures, such as choristeric patterns. We're going to see localized vortices that I will be explaining later in the presentation. And also, I'm showing here in the bottom row, as somehow a spoiler of the presentation, we see some simulations that we can try to do in order to explain what are the things that we can observe experimentally. So let's start with the basics. And the first of all is what are liquid crystals? So liquid crystals is a mesophase. That means that it's a phase that is between two different phases of matter, that is being a solid and an isotropic liquid like water. And the one that we are going to be first introducing are called nematics. So nematics are defined with a director vector, which is the green arrow that you can see on the left, which characterizes the orientation that the liquid crystal has. So in this example, in the case of the nematic phase, liquid crystal will have a defined orientation, nevertheless, will be spatially disordered. These liquid crystals are also characterized by anisotropic molecules, such as the one that you can see in the images, which are somehow like a grain of rice. Also, these liquid crystals that we're going to be studying are thermotropic. This means that we can change between these different phases just by changing the temperature at which we heat the liquid crystal. In our case, we're going to work with a special type of nematic liquid crystal, which are called chiral nematic liquid crystals. This is a different phase that we can create by including a chiral agent. In this case, and throughout the presentation, we are going to be using EOS-12, which was synthesized at the Universidad de Concepción by Dr. Jorge Vergara and Dr. Paulina Hidalgo. And this chiral nematics, the important aspect that it can differ from normal nematics is that whenever we include a chiral agent, what we're going to do is to create a helicoidal structure throughout the system and therefore breaking the mirror image of the system. So these chiral nematics can also be referred in literature as cholesterics and are the ones that I'm showing on the right, which has a defining characteristic, which is called the cholesteric pitch, which is the height at which this helicoidal structure can create a 2p rotation. And the important aspect of these chiral nematics, also apart from this cholesteric pitch, is that it can create the texture that I show you in one of the first slides. Now, to study them, I'm going to present the experimental setup that we are using. In our case, we're going to use a technique which is called the polarized optical microscopy technique. In this case, we have a sample which can be confined either inside a cell, or we can also put on top of a glass slide. And this sample will be inside a thermal chamber where we can try to change the temperature, and also we can change the heating rate at which we change that temperature. And this technique of this microscopy technique, what we do is that we put two linear polarizers, one above and one below, which is going to be P and A respectively, which is showing on the left. And we are going to illuminate this sample with the WLS, which means a white light source. We illuminate the sample, it goes through then an objective. We sometimes can use, for example, a quarter wave plate, which is represented by that lambda force that appears over there. It's not for every experiment, but later on the second chapter, I'm going to show the usage that we can have. And finally, the transmitted light will go through a CMOS camera. So in our case, what we're going to use in this confinement is going to use homotropic alignment. This means that the liquid crystal is perpendicularly anchored on the top and bottom walls of the inside of the glass cell. So for example, at the right, I'm showing the polarized optical microscopy technique on a chiral nematic liquid crystal, where every part of the system has the homotropic alignment, and therefore we see a dark image since we have cross polarization. Also, the little dots that you can see are glass beads, which are used for the manufacturer as spacers to keep the same height throughout the cell. So now let's try to introduce how can we achieve those textures that I showed before. And for this, we're going to be studying what is called the unwinding-winding transition, which in this case is that whenever we have this chiral nematic liquid crystal, and since I said before, we can change the temperature and therefore change the characteristic that the liquid crystal has. And therefore, if I change the temperature, in this case, as you can see on the graph at the top right, if I increase the temperature, the pitch drops. This means, at least geometrically, that this helicoidal structure is developing into the cell, and therefore we are going to go into another phase. We're having a phase transition between the homotropic phase to the TIC phase, or also called the translation invariant configuration, which is homogeneous throughout the system, which is shown at the bottom right as the image that you can see as blue. So now the question is, but how can we allow? We can allow the system to have those textures? And the reason that the thing that we can change experimentally is to change what is called the confinement parameter, which will be the defining parameter to achieve those textures. So the confinement parameter is the ratio between the height of the cell, the confinement of the system, and also the cholesteric pitch. So in the case of the pitch, it can depend between how many chiral agents it has the system. It can change with temperature or external fields such as a magnetic or an electrical field. And also that D over there will be the height of the cell. The reason being is because since we have a geometrical problem, then all the constraints will be also be geometrical. This parameter will be more explained a little bit throughout the second chapter also, where we play a little bit around this confinement. So as I showed before, we do have textures. I showed, for example, patterns. I showed, for example, these little bubbles that we observed that I said that they were a localized vortex. And what we are going to work in this presentation, and giving the presentation its name, we're going to talk a little bit about localized topological defects. So we have two types of defect. One that is with the patterns, which are the dislocations. So dislocations are a topological defect of the pattern, not the liquid crystal itself. And also we do have a topological defect of the liquid crystal, which is at the bottom. You see that chiral bubble that we called, or that little circle that you can observe at the bottom. And these two topological defects has also a topological charge. So they have a singularity in the phase, as you can see the figure at the middle. And they are presented by an integer number whenever we integrate around this singularity. So let me start with the first part of the presentation, which is called topological transitions between disordered patterns. So to explain a little bit what we are observing in the case of cholesteric patterns, we can create a little zoom of what is happening with the director. This means that we are trying to see how it's working the orientation around these patterns. And whenever we heat the material, that is, we are increasing the temperature of the cell via the thermal chamber, what we are observing is that the chiral nematic liquid crystal develops the helicoidal structure into the plane. And therefore, it starts to elongate, since in our case, what we're observing is that an helicoidal structure forms, creating what we call cholesteric fingers. So cholesteric fingers are the path that you can see at the right, which are that pink, the pink stuff that you can observe. And since we are using the POM and the director starts to move, get off the alignment, for the homotropy of the cell, we observe that imaging since the liquid crystal is birefringent, we observe the transmitted light. So now we do see that it has dynamics. Therefore, what we have are two different phases, two distinct phases. One, which is homotropic, like the image that I showed whenever I was explaining the experimental setup, and also one that has the cholesteric pattern. So now the question is, okay, what happens between them? Because the system has to somehow get from the homotropic alignment to the cholesteric pattern. And what we check experimentally is that we can find a temperature, in this case, 48 degrees Celsius, when the homotropic alignment is stable. We have only that type of phase. And then whenever we heat the material, we can find that also there appears a cholesteric pattern at 52 degrees Celsius. So we do have two distinct phases. And now the question is, okay, if we have an initial temperature and we do have a final temperature, the question now is, well, at which heating rate which will go, okay? So another characteristic, before I go to the next step, is that whenever we observe the dynamics, they nucleate the cholesteric fingers from the glass spacers. So we do know that they start to create these cholesteric fingers from the glass spacers. They go through the system. But now the question is, okay, how quickly should we go? And the thermal chamber allows us to try to change the heating rate. So we can go slow, we can go fast, and we can try to observe what happens between it. So I'm now showing two examples. The one of the left is accelerated 64 times, and the one of the right is accelerated 3 times. So, for example, at the left, what we observe is that if we go very slow, these fingers will nucleate, they will start to go through the cell, and they will have some transversal instabilities. Therefore, it will start to undulate. Nevertheless, if we also see the one of the right, it tries to follow the same path in the beginning, but now the tip swells and divides and creates a bifurcation, and therefore it has now two types of cholesteric fingers that emerge from the tip, and therefore we can see that we have, just by changing the heating rate, two distinct phases. One that does not have any type of dislocations, does not have branches, and the one of the right that you can see as the branched pattern that has a lot. So now, let's try to characterize the dynamics that we observe. And in the case of the material that we're using, let's start, for example, with 0.1 degrees Celsius per minute, and let's start to go faster and faster from this 48 degrees Celsius to the 52. And what we observe is that in the cholesteric pattern, more branches start to appear, okay? So now there are these two mechanisms, transversal instabilities, and we also have the splitting and side branching, for example. And we observe that as we start to heat, these mechanisms start to change from the transversal instabilities to the branches that we observe in the branching patterns. So if we want to characterize this transition, we are going to somehow highlight these locations. These are the ones that start to emerge whenever we are changing the heating rate. And what we can do is some image processing around the cholesteric patterns. We initially, what we do is that we cut a piece of the cholesteric pattern. We then go to make it a grayscale, and then we binarize it, okay, which is at the bottom left. Finally, then we skeletonize it, the pattern, and therefore we only have matrices of 0 and 1s, and we can just find the triads in the system in order to find the dislocations. If we count the dislocations for each step that we are changing the heating rate, what we're going to observe is that we find a transition which is continuous in nature. We can characterize the transition by being a supercritical transition, which is noisy. The reason being is that we have inherent thermal fluctuations into the system since we are heating it. It's not completely homogeneous, and therefore sometimes branches can emerge. So this noisy supercritical bifurcation is determined by the magenta line that you can observe. And from the formula that you can see also in magenta, we can try to eliminate all the noise terms, for example, in this case being B and also N sub 0, and therefore obtaining a deterministic transition, which is a supercritical without the noise, which is the green line, the green dotted line, which can divide in its zero the two phases, in this case, the imaginative region that is colored red, and the one that is branched, which is in blue. So now we observe the transition, but now we want to model it. We have to do physics around it. And to model this liquid crystal, what the people generally do is that they work towards the Frank-Ossie free energy, which is represented in the left, which accounts for the elastic deformations that the liquid crystal can have. So in this case, there are three. There are the three Frank constants, which is called splay, twist, and bend. And this we can derive the one that is called Frank-Ossie free energy, which is with the letter F. And that free energy, what people really do is that it minimizes the orientation that the director can have, and therefore it can create these textures. Nevertheless, the dynamics is very difficult for this type of work because it's very computational heavy, and also it cannot be able to explore very much of the dynamics since the director can sometimes lose its properties. So now, what we can do and somehow try to explain this throughout a physical system is that first, let's consider that the liquid crystal have dissipative dynamics, and therefore we can derive the equation that you have at the right, where gamma in this case will be the rotational viscosity of the system. And in this case, we also are imposing that the norm is conserved. Then we impose an ansatz, in this case is an ansatz for the director vector, which we're going to project into the plane in order to try to explore it as a two-dimensional system. We have to remember that we are using a microscope setup, and therefore we are observing from above. We are observing something somehow in 2D. We are going to try to account for the dynamics that we observe. And finally, we define an order parameter, which is in this case A, which is a complex order parameter, which will be able to give us the information about the dynamics of the liquid crystal. So let me start with a phenomenological model that it was first derived as a symmetry arguments, and later it was derived also from the Frank-Ossie free energy directly. And in this case, what we do is that we first explore a little bit about which type of transition we do have in the case of the cholesteric phase. And we observe that from the homotropic state, which is shown at the top right, you see that whenever we hit the material, you can observe that we are looking at the transmitted light. Whenever we hit the material, the cholesteric pattern will start to emerge, which is shown as the orange line. And then whenever we get to the cholesteric pattern, we just start to cool down the system, and then we get back to the homotropic state. This shows a discontinuous transition and hysteresis curve. And therefore, what we do have at the end of the day is a Gibbs-Landau equation, which has a kinetic nonlinearity in order to support the hysteresis that we observe. So in this case, as I said before, A is a complex order parameter, and that partial eta of bar eta is just the Laplacian, which in our case, we're using the Wirtinger derivative, which is a complex derivative. Nevertheless, we are working with a chiral liquid crystal, so we want to account for the chiral part and the liquid crystal part. In the case of the liquid crystal, we do know that it has an isotropy, and therefore it has a connection between the term that you can see over here with delta, which in this case accounts for the anisotropy of the system, and also we do have also another term which is He, which is the one that accounts for the chiral effects of the system. Okay, so whenever we include these two systems in our model, we are going to have what we call the chiral anisotropy against Landau equation. Now, we do have the experiments, and we observe that we have an initial condition. In our case, it's the glass bead. So we know that from the glass bead, the cholesteric fingers emerge, they nucleate, and they create the pattern. And now we have to account for it. So in our case, what we are going to do is that a topological equivalent in our case will be using a localized vortex. The reason being is that since we have an entropical alignment, we expect that surrounding the glass bead, we do have perpendicular anchoring, therefore acting as a hedgehog. And since that will mean that we have into the system a topological charge, we can create a localized vortex in order to emulate that type of behavior. So what we do is we put a Rayleigh condition, in this case, a localized vortex, which is shown at the top left and the top right, which are two ways of representing the complex order parameter that I explained later, before. The one at the left, which is the amplitude of the system, and the one on the right, which is the polarization field, as we call it, which it looks a little bit more to the things that we observe experimentally. So what we're going to do is that we start with the localized vortex. We then find into the phase diagram where we can observe some dynamics that can be emerging into the system, and we observe that from an initial condition, in this case, that glass bead that will be the localized vortex, will emerge the cholesteric fingers and create then a pattern. Then we have to play again. Let's start to put some localized vortices. We see that in the experiment we have some glass beads all around the space. Now we can do the same, but in this case as a simulation. We look at the phase diagram, and what we can see is that we found two different phases at which these two patterns, the ones at the left, which are called invaginated patterns, and the one at the right, which is called branched patterns, can be found. Okay. So now we know that this model that we use has at least the equilibria, and now we want to see if it can also have the other types of effects or the transition even that we observed before. Nevertheless, we have to show some parameter. Now we want to try to connect somehow the experiment with the simulations, and for that we have to find a parameter that we want to move in order to be our bifurcation parameter. So that is a little tricky, and we do have two parameters. So at the right, you can see our phase diagram, and you can observe that we do have two different variables. One is called mu, the linear parameter, and the other one is called He, which will be the chiral parameter. So which one we will like to move? In this case, we are going to move He, and the reason being is that what we do know is that since we cannot measure directly the pitch, the cholesteric pitch, what we do know is that by observing the cholesteric pattern, we know that somehow the cholesteric pattern is a representation or manifestation, if you want, of the cholesteric pitch. So since we do see that the helicoidal structure develops into the plane, we can try to check for the characteristic length of the pattern. And if it changes whenever we also change the heating rate, we can try to connect both. At the bottom left, you can observe the characteristic length of the pattern, which is micrometers, the distance between these cholesteric fingers, and the heating rate. And what we do observe is that the characteristic length starts to drop as we start to heating up the material faster. So what is the conclusion? Is that if with the branched pattern has a lower characteristic length, we can try to observe think a little bit that the manifestation of the cholesteric pitch will also be shorter, and therefore for a shorter characteristic length, we also will have a shorter pitch. And since He is directly connected with the cholesteric pitch, we thought that He will be the most appropriate parameter in order to do the bifurcation. So we can find, as I said before, through the phase diagram, the invaginated region, the branching region, and now we want to go slowly to see if we can see the transition. And we do in fact observe the transition. So what we do is that we have the experiment, we include some noise, some additive noise with the simulations, and we start from the invaginated region. As we increase the parameter He, we observe that we are going towards the branching region. So we do have the same type of transition, We have a supercritical transition, which is noisy. And now the question is, if I said before, patterns are ubiquitous, well, then we should expect that we can also observe this in other systems. Thankfully, there is a way to try to check for this and account for this, and this case will be to study somehow the universality of this transition by using something that is called a prototype equation for pattern formation, which was derived by Professor Chilidi, and also it was derived by Stefania and Professor Fleck, which is called this prototype equation, the numberation as we Hohenberg equation. The importance of this equation that lies on the fact that it has been derived on different types of fields, in this case, biology, chemistry system, material science, optics, and also chemistry. I think I said that before. But the important aspect is that there are a lot of models that can be derived from this one. Therefore, if we work on the non-variation lossy Hohenberg equation, we can expect that maybe other types of systems will also exhibit the same transition. So just to explain a little bit the equation, we see a bifurcation. We also do have diffusion and hyperdiffusion, which will be the typical Hohenberg equation. And whenever we create a symmetry between these two homogeneous states, we are going to account for two terms, which will be the drift and the diffusion, which are just corrections. So
Hola.
So Victor will appear sooner. Okay, don't worry.
necesito que prenda, profesor, acepte la. ¿Sí? Okay, hello, you can hear me?
¿Puedes
Sí,
hablar,
sí.
Víctor?
Yes, yes.
Thanks. Okay, I will
Listen
continue.
to you now.
Okay.
Okay.
I will continue with the presentation. So at the first chapters, I will resume. The conclusions that we have is like experimentally and numerically, we observe a supercritical transition. And then we observe that this topological transition at the end of the day, since we're observing that these thermal topological excitations start to emerge into the system as we change the heating rate, we have that by having the same initial and final temperature, we observe different states that can be accessed through the heating rate. So we characterize the transition. We have some universal properties, and now one of the questions that we can try to ask for us is what are the next steps that we can be working on towards this objective. And first is will be to, in the case of the liquid crystal setup, it was to start to continue exploring what can happen with the heating rate. It has some very interesting applications, and therefore we can try to work on that, and also continue testing the universality of this transition. For example, at the left and the right, we have some very preliminary results on the Gray-Scott and the Fitzhugh-Nagomo equations. And finally, we can also consider another types of effects, in this case, curvature, for example, or we can also have these process-dependent variables that we explore in this work over here. So now I will go towards the second chapter, which is called Abricos of clusters in current liquid crystal droplets. So a little bit of historical context. So the abricos of lattice was first proposed by Professor Alexei Abrikosov in the 50s, where in type 2 superconductors, whenever a threshold was passed with the magnetic field, then the magnetic field will be able to penetrate a type 2 superconductors, creating what we call fluxions, which is the quantized part of the magnetic flux. And these type of fluxions will account for localized vortices, which will interact, and therefore it will self-organize into what we call now the abricos of lattice, or a triangular lattice of localized topological defects. So at the right, well, at the center left, just right to the abricosov, you can observe the abricosov lattice in two superconductors, and later in different groups, it was tried to do some analogy between what they observed in superconductors and, for example, Bose-Einstein condensates. When in group of Kegel, they managed to create these lattices by steering around a condensate with a laser. So we observe that these effects should be also has some universal properties. Therefore, if we see another systems, we try to expect something similar. And the question is, can we observe something similar? Yes, in this case, dissipative dynamics, since both superconductors and in Bose-Einstein condensates are conservative media. So what should be our recipe? We have to do something simple in order to understand this. And in our case, we are going to be characterizing the system towards two main objectives. First, we need that these localized vortices should have some short-range interactive repulsion, okay? Therefore, if I put two of them very close, they should repel. That part will be already be done since chiral domains and the system, well, is chiral. Therefore, it will choose one of the topological charges, in this case +1, and therefore every charge into the system is +1, which we would like to try to characterize interaction, but at least that part of being repelling is well known. The part of the right is a little more tricky. It's a little more difficult since we now need to cluster. We need them to group them in order to create the lattice, because that interaction must be done. And that part is not very easy to do. And there's some groups that they have been trying to do that. Since before this, chiral domains are very well known. They're known from the 70s. In a lot of Japanese groups, they were working on chiral domains. They observed these textures, and whenever they saw a lot of chiral domains are around the cell, they observed that they will create the lattice that we can call abricosov lattice if you want. Nevertheless, that is not controlled. It's very difficult to try to create the lattice, which we can only hope that we can find this arrangement. And lately, some groups, for example, in the case of University of Colorado Boulder, led by Professor Smaljuk, they have been working on some ways in order to control this type of chiral domains. For example, in the left, you can see an optically manipulated pitch, and therefore they can create an inhomogeneous plane in order to be the pitch preferred in some places in the cell than others, and therefore what they observe is that the chiral domains migrate towards the laser. That are the examples that we found. Another type of example that they used is by creating another type of holding structure. So by also using a laser, they were able to create another type of localized effect, which encloses these type of chiral domains. So what they call also a chiral skirmion path, okay, which are the ones at the right in yellow. Nevertheless, these two methods of trying to create the lattice is very difficult. So we cannot work in this case optically. We can try to create another way, maybe more appropriate, because chiral domains at the end of the day, they are being used in optics, and they have some technological applications. For example, they have been studies that they show that they can be worked as microlenses. So for example, they can focalize the light of a laser, and also can be used as phase gratings if we, for example, impose a perpendicular contact with the laser. So we do have some technical applications which have not been yet explored, since we do not have a very good control of these systems, or arrangement if you want. And we do have a way of doing it. And for that, we're going to go a little bit back of the presentation. I remember that the most important parameter that we have is the confinement parameter. So the geometrical constraints that also another type of group try to work with. Whenever they change the optical setup, they also change the confinement parameter in some way. So what we can do? We know that, for example, at the top left, you see all those chiral domains that are interacting, but that is just luck. I just heat up the material, cool down the material, and we observe these textures. Nevertheless, when you really observe is what we observe at the bottom left. You see some chiral domains all over the place. And the question is, okay, what happens now if instead of changing, for example, the pitch optically, and we try to do some type of a confinement effect, we change the homogeneity of the cell? Because since the chiral, in this case, the chiral material crystal is confined into a cell, we can try to check what happens, for example, if we put a droplet. Since now we do have some material in some parts of the droplet, we expect at the center, that, for example, to the side. So maybe a droplet will be a good idea in order to promote the confinement parameter as something that depends on the coordinates of the system. So what we found out is that we observe what we call now the abricosov cluster in liquid crystals. So exactly by creating these droplets, we observe that the chiral domains migrate to the center of the droplet, and they create a triangular lattice since the self-organization start to start to work. So in this case, now in the figure of the left that has an orange bar, diagonal bar, orange bar, we are using a quarter wave plate in order to check for the outline of the droplet. And at the right, you can observe, for example, the figures at the top right. We have two different droplets which has different amounts of chiral agent into it. And at the bottom, we see different droplets also, but with different amounts of chiral domains. So, as I said before, our recipe, we have to explain both type of effects. The first, interaction. In our case, what we're going to do is we are going to start by using what we call bipolar coordinates in order to properly create both solutions, sorry. We are going to create solutions very far apart. We are going to make the answers that you can see on top. And we are going to consider that these chiral domains are sufficiently separate. We have to linearize on the corrections that we're using. And imposing a solvability condition, we are going to derive, if we also said that delta will be the distance between the chiral domains, we have a kinematic repulsion law that we derive, that is the one that you can observe at the bottom. So this means that with time, these chiral domains will repel logarithmically with the distance we repel between them will increase logarithmically. So the kinematic repulsion law, we can observe it. We know now that it is repulsive in fact, but we now need to know somehow to account for the confinement. So since now we are using a droplet, we are no longer using a cell, we should expect that all the parameters in our equation, for example, we have the linear, the beta, he, we also have delta, should now be promoted to an inhomogeneous parameter. Therefore, since we do not have the same amount of material in every part of the system. Now we have to choose one, the same as the chapter before us. So if we do a multi-scale analysis in our case, we can check for which systems can be perturbed the most by whenever I impose, for example, at a parameter that depends on the spatial coordinates. And whenever we perform this analysis, we observe that the mu parameter, the linear parameter, will be the one that is most affected. Therefore, we can only promote the linear parameter and we can leave the rest parameters like a constant parameter. Nevertheless, they should be also inhomogeneous, but we are going to approximate into the linear parameter only. And finally, we can observe that we only need to account for something that groups these chiral domains together. So we can just account for a parabola in order to see what happens. So now for the confinement effects, what we are going to do is we put now the same ansatz. Instead of putting two vortices, we are just putting one. We are putting this into this system, which has this specially promoted linear parameter. And what we want to observe what happens. So for example, here I put some simulations. We do a similar analysis than the one that we did before. We work a little bit towards where it is, this localized spot in our simulation, and we observe that it starts to migrate towards the center. For example, at the bottom right, you observed a small animation of these chiral domains that are going to interact, and there is a point, since they start to engage in this short-range repulsive interaction, that they will be stable. So now, let's try to do some numerical simulations. What we can do is let's put on top of the numerical grid a lot of these localized vortices, and then we start to observe the dynamics. We impose the confinement through the promotion of the linear parameter, and we observe that, in fact, all of this chiral domain will start to migrate towards the center of the droplet, creating what we call the Abrikosov cluster. Okay? So, as conclusions of the second chapter, we observed experimentally the formation of what we now call Abrikosov clusters. We theoretically accounted for both the repulsive interaction and the confinement effects. And numerically, we observed that we are in a good agreement with the experimental observations that we have. And finally, as perspectives, in the second chapter, we can create, for example, now, if we have these droplets that can be used for it to somehow drive this migration of chiral domains, we can control them. And therefore, if we change, for example, the shape of the droplet, we can try to create different type of arrangements. For example, here I show a plethora of different droplets. And we can try to create another types of effects. For example, we can photopolymerize the droplet in order to fix it and create, for example, a device instead of being in this liquid crystal phase. And finally, since the Gibbs-Landau equation can also be derived from another type of system and is very similar to conservative system, for example, chiral magnets, this type of approach to work to create this Abrikosov cluster can also be used, maybe, for example, to understand what can happen in those systems, such as magnets. So I want to thank all for your attention, and also a special gratitude for the team, my advisor, Professor Marcel Clerc, Dr. Gregorio González Cortés, and Dr. Sebastián Echeverría, who worked with me in my master's. And also, finally, a special gratitude also for our chemistry team in Concepción, led by Dr. Paulina Hidalgo and Dr. Jorge Vergara. Thank you very much.
Okay, so now we move to the second part of the presentation to move to the committee questions. So we start with maybe a gender argument. So we will start with Paulina. Paulina, could you start?
Okay. Do you hear me good? Yeah.
Okay. Yeah, you're okay.
Yeah. Okay. First of all, I want to congratulate you, Victor, on both your work, your whole work, and your presentation. And to start, I want to ask you a very general question first. What was the main motivation that led you to research this particular topic?
Oh, okay. So, well, my main motivation is just that I really like liquid crystal. I think that they are beautiful. I think it's very important, at least for me, it's very important to like the experiments that I did. I remember that I got in love with liquid crystal experiments whenever I did my my practice here in the university. I observed the textures and I really engaged with them, and I wanted to explain them, and then I want to work on this topic. I really liked it.
Okay, thank you, Victor. I want to start to the first chapter. And in this context, I would like to ask you, would you have the same results with any chiral compound in your mixer?
We should expect a similar result. The reason being is since the confinement parameter will be the one that be changing, since now the cholesteric pitch will change. This property at the end of the day is inherent for each mixture that we do. We have observed the same phenomena, for example, with EOS 12, but at different concentrations. I did not make I did not put that on the work. But we should observe the same since it's a geometrical argument, the one that enables the system to have this type of effects. So it would be also interesting to see if we can start to explore a little more about the generality, the universality, sorry, about the problem. But yeah, we should expect the similar results.
Okay. And what happens if a finger doesn't form from a spacer?
Okay, thanks. Allow me to now share my presentation again. So in the case of fingers, whenever they emerge, what we do observe in our experiment, in our case, since we are going very slowly, we observe that these cholesteric fingers will nucleate from the glass bead. They will start to go into the system, create the cholesteric pattern. But it's not the only way that these cholesteric patterns can emerge. So what we observe is, for example, if we go faster, that's not to 1 degree Celsius per minute, but for example, 5 degrees Celsius per minute, or even 10, what we do observe is another type of thing. So for example, here I'm showing a video. Now I will start it right now. So what I'm doing right now is that I preheat the thermal chamber to 54 degrees Celsius, and then I place a liquid crystal cell that is at room temperature. There I put the liquid crystal cell. So now this 18 degrees Celsius cell is now being in contact with this 54 degrees Celsius thermal chamber. This rapid heating of the material will be able to create cholesteric fingers in parts that the spacers are not the only point that they be created. For example, here you can see some points over here, for example, that you will see cholesteric fingers that will emerge only by thermal fluctuations in the cell. So they do have some other types of properties. For example, they do have, for example, now a pointy, the cholesteric fingers is pointy in one of the ends, not only rounded, which is aligned with the topological charge, since that pointy tip is usually connected to the glass bead. We do not observe that part, but in our case, since in this case, if we are hitting very fast the material, we observe the cholesteric finger emerge, and since it's no longer connected to the glass bead, this cholesteric finger with the pointy tip will start to elongate and try to find another cholesteric finger to interact, and it will connect by creating all these locations.
Okay. And could you please go to the slide 15?
Okay.
Okay. Could you explain in more detail the formation of the invaginated and branching patterns? And why do they arise at the same temperature but with different heating rates? Could you
Okay,
explain a little bit?
yes, of course. So as I'm showing on the right, you see that we do observe these two type of mechanisms. To try to explain it a little more physically, is that what we observe is that first of all, the system, since it's variational, it wants to try to create the equilibrium of a cholesteric pattern, and then it would fill up all the cell with the cholesteric pattern. So the system wants to create this pattern, and it has to find which method is more useful in order to try to cover, now I remember the word, cover the full cell. So if we are going very slow, what we are doing is that the injection of energy that we are imposing into the system is also very low, okay? So now the system will try to elongate in order to create a cholesteric pattern, but it does not have now the sufficient energy in order to split its tip and create branches. Branches will be the mechanism that favors the system to create the cholesteric pattern. But since it does not it is not able to access to that energy, it can only create transversal instabilities, which are not preferred, but are the only thing that it can do in order to create the cholesteric pattern itself. If we go faster, now the system do have access to the tip splitting or side branching mechanisms, and it can cover up the system in a more efficient and more quickly.
Okay. For the second part of your presentation, and could you describe the experimental setup used to study the structure formation within these droplets? Maybe I don't have any slide for tell you maybe for start.
Maybe I will start for this one.
Okay.
So in our case, the experimental setup was the following. So we had a glass bead. Oh, sorry, not glass bead, glass slide. And what I do is with a micro pipette, I just take a little bit of chiral imaging liquid crystal, and I slowly put it with my hands. I put it on dribble droplets into the glass slide. Now that does have a problem. So is that I am not able to control the sizes, neither the shapes, since I do it by hand. Nevertheless, that could be improved. And whenever we put the material, we should expect that around the curvature of the droplet, we observe that the director is anchored homeotropically. The reason being of what we do believe on this is that at the right, you can see that some droplets that are bigger in size has what we observe a vortex, as a type of vortex at the walls of the droplets, which are for example, the figures that you can observe at the bottom right. You can see at the background of the chiral domain, you can see this vortex, and therefore we can expect that it has some type of homeotropic alignment into the droplet itself. So, and also, since the glass slide we are not treating it in any way, we also do observe an homeotropic alignment, and that is the reason why the droplet that I showed before has those director anchored. And yeah, we only just put the glass slide. We put by capillarity all those droplets, and then we study them under the polarized optical microscopy setup. Finally, if we want to now create these chiral domains into the droplet, what we do is that we heat up the material to the isotropic liquid state, that is heating up for around 70, 80 degrees Celsius, and then we cool down the material to room temperature, and what we observe is that the chiral domains emerges and create this abricosal cluster. Well, nevertheless, we are not able to observe the dynamics of these of the chiral domains itself, but we do observe the equilibrium.
Okay. What other kind of self-organization of topological defect could you explore it in chiral droplet systems?
Oh, okay. There are many. So that's a good question. Maybe I can show you some before. So chiral domain is one of many types of topological defects. For example, one figure that I didn't explore very much and in this dissertation is the third one in the top row. What you can observe are some rings. Okay, so this type of rings are another type of topological defect that can emerge in these systems and can also be created with heating and cooling down the system with another type of chiral concentration. So the confinement also changes. But this type of rings accounts for another type of topological defect. So therefore, we can explore also these rings in our case. If we are able to also try to introduce optically created topological defects, there are another type of more complex topological defects, such as lignotons, which are created also, for example, by the group of Professor Smaljuk, can also exhibit similar self-organizations. So there are a lot of topological defects that should exhibit similar dynamics.
Will be interesting to study this kind of textures in a TGBA phase.
Yeah, sure.
But it's very unstable in a very short range of temperature, but maybe would be interesting. Just
sure.
Just for an idea.
Sure.
And let me see. Okay. What conceptual challenge were the most difficult of overcome during your thesis work? Or this was more difficult for you?
The most difficult challenge, well, I think it would be to create the abricos of the abricos of clusters. So as I said, they were done by hand. So, and I do not have the best of affinities for these type of effects. Nevertheless, maybe here I can explain it a little better. So you see that scale bar is 150 micrometers. So that is a very small droplet. So I think it took a long time to grade all those droplets, but it was a very fulfilling experiment. So it was a very nice experiment to do. I learned a lot by doing this experiment. But as a challenge itself, I think it definitely was to do the experimental abricos of clusters. I think that was the most difficult one.
And if you repeat this experiment once and again, do you have the same result all the time?
No, I have never had the same result. But I think the important thing is to create, well, a lot of different type of droplets in order to try to check and try to somehow have an advantage of having so many droplets, because by having these irregular droplets, we also learn a lot. For example, as I show in the case of different droplets, let's say, for example, the one that I show over here, we observe that, well, the confinement works. And therefore, if we have, for example, an elongated droplet, which also was done, well, not because I really wanted to, but it happened. We observe that these chiral domains will align and be in line also. So now all this exploring that we did in chiral domains was also being enabled by these irregular type of droplets that we done by hand. So it's a mixture of pros and cons that by using this type of manufacturing. Okay, so yeah. To respond to your question, yeah, no, there were no droplets. There were similar droplets, but I think each droplet is different. So if each has their own special spot.
Okay, and my last question in the same slide, in the point 2, do you have some idea how do you come to do this?
Yeah, we do have materials. We do have a material. What we can do is that we put some molecules that are able to photopolymerize. Now, I do not know the details of how the process has to go in order which amount we have to do. We know that we have to put very slow amounts, at least the articles that I have been reading about, of these photopolymerizing agents into the system. Then with the material, what we have to do is that we have to somehow freeze it. We have to photopolymerize the material with using UV light. And then we can have this like a plastic device at the end of the day, which should have the same structure which we observe as abricos of clusters. So right now we do not have the ways in order to incorporate this type of agents into the droplet, but it's one of the things that we want to do.
Okay, thank you, Victor. Thank you, Marcel. It's all for my side.
Okay, thank you, Paulina. Now we move to, we use the criteria of the distance, so we move to Professor Kihu from China.
Hi, Victor. It's can you hear me? Is it good? Yeah. It's a lot of work. It's very comprehensive. So I have several questions to ask you. When we look at this, fingerprints, that texture in the first part, And one that pattern that is like you very similar to some of the dendritic growth, or the this left top one.
Yeah.
Are these patterns of fractals? That has a
I
fractal
rem
dimension, positive dimension.
I remember once that I was checking about the fractal dimension of this type of system by using the box counting method, but we had never checked or do a very good check in this case. Even if we see branches, we do not see dendritic type of growth. Dendritic type of
Okay.
growth would be more similar to the ones that we observe, for example, whenever we hit the material very fast. I do have a video, so it is the one that I showed before, so maybe here I have it. So in this case, whenever we hit the material very fast and these thermal fluctuations are enabled to create cholesteric fingers in places that there are no glass bits. So
Mm-hmm.
and go a little faster. What you can observe, for example, here is that, as I
Yeah.
said, there is a pointy tip on the cholesteric pattern. So as we start to increase, for example, we observe here, you see the dendritic growth. As the cholesteric fingers start to go into the system, it will have these branches around it. So maybe it would be a good idea to try to check for the fractal dimension. The box counting method should work. It may be a little difficult since the system is disordered, but that is something that we could explore.
Okay. So I want to follow up on the Paulina's question about the you have two instability types in instability. One instability is that bending of the fingerprint texture, and the other is tip splitting.
Yes.
So do you have any clear picture why these two types of instability, right? What is the driving mechanism? My understanding is that this fingerprint that I want to go bigger in terms area. So so what is a kind of, do you know what is a instability causing this tip splitting or causing this bending?
Okay, so there was a study before me, which was performed by Dr. Sebastián Echeverría, which was one of my collaborators, and he showed that whenever the cholesteric finger has sufficient energy, in this case, the tip will swell. So, for example, on the bottom right, you're going to observe, for example, the cholesteric finger. At the top and the bottom, in both cases, we see the cholesteric finger, but at the bottom, the tip is more swell. It's a little bit more swell. It's not very much the difference.
Okay.
But what will end up happening is that this tip will start to swell and it will divide. Here it is not very well shown, but maybe here at the bottoms where there are some side branching, where these in curvature points, these cholesteric finger will nucleate, we will observe here the tip splitting mechanism. So to maybe recover a little bit of what Paulina asked me, is that whenever we heat up the material, what we are doing by changing the heating rate is changing the way that we are injecting energy into the system. Okay?
Yeah.
The system wants to do one thing, and is to try to create a cholesteric pattern. It tries to fill up the material into the new equilibria that we are imposing by having the system into 52 degrees Celsius. So if we are injecting very slowly the energy, and the system will not have sufficiently energy, the cholesteric finger will not be sufficiently energized in order to split. It is tip in order to cover up the system more efficiently. And therefore, the only mechanism that it can be created are these transversal instabilities that can emerge.
Yeah. Can I understand in saying that the top one, the transversal instability and the tip splitting, they are similar, but the only difference is that the transversal instability has a larger wavelength than this tip splitting.
Okay, so in the first case, yes, that is that is one of the characteristics that it divides. But the main focus on the presentation was that in the case of whenever we are getting into the new mechanisms, dislocation will emerge. And as I explained in the localized topological defect slide, these locations are a topological defect of the pattern, as a pattern, not as a liquid crystals. So therefore,
Okay.
whenever the pattern creates a dislocation, we account for a new topological defect that it emerges into the system. So that is the reason why we said that these transitions that we found are topological in nature, since these locations are being generated as long as we are changing the heating rate. So the most important aspect between the invagination and the branched patterns are the emergence of these dislocations.
Okay, so I have two more questions. The other question is that when you're talking about the universality, right? The universality class, that you purely rely on this number of topological defects as a function of temperature. Is that right? No. Yeah. So the bottom one. So, right. When you determine this, right? So you fit this dashed line. That's you're fitting with your theory, right?
Yes.
So there's a question. So technically, right? So when you do numerical calculation, it's this very difficult to set the threshold value. If you change the threshold value a little bit to the left, and the exponent could be different.
But what do you mean about the threshold value? I'm not understanding that part of the question.
This vertical line, that how do you set the vertical line?
The vertical line, do you mean the one over here? Sorry, the exponent here, Professor Wei? I don't know if you can see my mouse.
Yes, I understand. Can you hear me?
Yes, I can hear you. So this vertical line. Yes?
Yes.
Okay. So the vertical line, what we do is that to account for the vertical line, what we do is that we have to find the deterministic curve. So by counting the topological defects into the system, so what we do is the reason why we have an error bar is that I put different types of disturbed spots. In this case, the Zwi-Hockenberg equation is not a complex field, is that U is a scalar parameter. So what we do is we put a disturbed spot, okay, a perturbation, and then we make the system to develop this type of pattern. Now, then we process the images in a very similar way than the ones that we had for the liquid crystal experiment. We count for these locations around the pattern, and then we found this that is in the black spot over here, that we fit it first with a noisy supercritical transition, which is the magenta line. Okay, so very fast, I will just go and show what happens in the case of to recover a little bit the equations. That magenta line is defined by the magenta formula. Okay, so that formula represents a noisy supercritical transition. That noisy part, in the case of the experiment, will be the thermal fluctuations. In the case of the numerical simulations, will be additive noise. If we remove the noisy parts of the formula, that is being this term over here, B and N sub 0, we are getting this formula over here, which is the deterministic curve that has the same parameters as the one that we found for the supercritical.
You mean the solid line? Solid line is that you have N0.
Yeah, in the magenta line we have N0. Okay. In the green one we only have the deterministic behavior of the system, and then we have the root. And in this root, we have the critical, in this case, hidden rate, at which we found the transition. That is how we can find that vertical line.
Yeah, that's clear to me now. Thank you. Final question. So in your second part, you're saying that your chiral domain clusters are Abrikosov lattice.
Yes.
How these are related to Abrikosov lattice? That I didn't get this similarity. Why this is Abrikosov lattice?
Okay, so there are two main motivations. So, well, maybe three. The first one being for historical reasons. So Abrikosov was the first one to propose the formation of these self-organized lattices of topological defects, which was later found in type 2 superconductors. Now, they are not only connected with the fact that Abrikosov found this type of lattices, but first, these lattices are triangular lattices of topological defects. We can find other type of lattices, for example, square lattices. In the case that we have +1 and -1 defects, we can have on another type of lattices that we can drive. But as a self-organized lattices, where every single one of the topological defects is has the same charge, we observe the minimal configuration, which in this case is the triangular lattice. So
the similarity between these two, your system and Abrikosov lattice, is that this lattice that is vortex lines that are also a topological defect line.
Yeah, exactly. We have
Okay,
topological
so
defects.
these are means that the Abrikosov lattice means that you have a lattice of topological defects. That's it, right?
Yeah, and also we do
Or,
have
or
another argument. Maybe I can go very
Mm.
fast about it, but that both
okay.
conductors and Bose-Einstein condensates have been is theory that is subjacent of the experiment is with Gibbs-Landau equations. They are similar to the ones that we use, but instead of having dissipative dynamics, it has conservative dynamics. But type 2 superconductors are explained with the Gibbs-Landau equations, and Bose-Einstein condensates can be explained with those equations. In our case, we use a similar method, and therefore, for those similarities is the reason why we call it an Abrikosov cluster, because we do not have a lattice, we have just a very discrete amount of localized vortices.
Okay, so the mathematical description of these two systems are similar.
Yes, it's also similar.
Okay, thank you. So I have no further question. Thank you.
Thank you, Professor Quiju. Now we move to Professor Emiliano Cortés from Germany. Emiliano, are you there?
Yes, I'm here.
Hello.
Okay. So thank you very much, Victor. Very nice work and a lot of work. So I have some questions, which are a bit of follow-up from previous questions, because they are like similar to what it has been already asked. But so for the first chapter, I think I will come back to some things that Paulina touched in her questions. So I didn't get, but you already explained this. So I didn't get why the rate of the heating you would think could influence on the final pattern and these things. But I think you already mentioned this, so I think we don't need to come back to this. But related to this question, maybe it's, and this is an open question which I don't have the answer. So could you think on a system in which you start with the same material and at the same temperature, but you have two different patterns? So would be the possibility that at the same temperature you can create two different patterns by changing things? I don't know. This is the question, like what you can change to change the pattern if it's not the temperature.
Okay, so well, that's a good question. So in this case, the reason why the temperature is very interesting to work with us is because we have a heating rate.
Yeah.
If we do a voltage, for example, analogy, it's a little more difficult since voltage will be an immediate effect of the system. We do not have an analogy in this case for the heating rate. Nevertheless, maybe also to try to answer the question, the first question, is that I think even before asking ourselves for materials, you can think about your hands. So for example, let's say that you're very, very cold, and then you put your hands very close, for example, to a fireplace, okay? So if you're very cold and you immediately put your hands between your in a fireplace, you will feel, for example, a tingling sensation, which is called the pins and needles sensation, right? So that's we sometimes not everyone likes. That sensation is being created because since the change of temperature is so big that the nerves of the system, they have to adapt very quickly, and that is the reason why you feel that. Nevertheless, if you start to go slowly and you start to slowly going your hands into the fireplace, you will see that sensation doesn't appear. And the reason why is because your nerves in your fingers are starting to adapt to the new environment. So the reason why we do have two mechanisms, and we do, for example, is that if we go fast or we go slow, we give the system more or less energy injection, okay? So to find an analogy, maybe we do know that in the case of a voltage driven system, for example, if we use voltage to have the cholesteric patterns, they have been observed, they observe, for example, imagination patterns. We tried to emulate that. We were not successful, but it will be very nice to find other types of material which we maybe can have an analogy. Probably the most direct material that can have a similar equilibria, but not dynamics, will be conservative systems such as chiral magnets. Chiral magnets also have cholesteric, well, not cholesteric, but they do have patterns in the case of chiral magnets. So maybe, for example, if we heat the material or we change some properties, we can find a similar transition. So I think from the works that we have been observing in the case of chiral nematic liquid crystals, the most immediate material that we can work now will be chiral magnets.
Okay, so but then at some point, what you're saying is that there is some hysteresis in the system, right? Because you may reach to the same final temperature, but through two different rates, and then the final pattern will be different.
Yes. Yes, maybe let me go to that slide. Here it is.
Mhm.
Yes. Yes. So
Exactly. Yeah, so this was around my question, like that you may reach the same final state, but the heating rate may influence how you reach there, and then like you will end in different patterns. So at the end, you start from the same system, you end up in the same temperature, but you end up with different patterns.
yes, yes, that is the reason why in the case, for example, voltage is a little difficult because we start with the, for example, for an initial voltage when we see the homotropic state.
Mhm.
We do not have something to change these the properties of the system since we can only impose, for example, the new voltage. We
Mhm.
know that there are ways in order to create an invagination pattern and another ways to create a branched one. Now, how can we go from one to another, for example, without using the heating rate and another type of variable is something that we can explore. We do not
Mhm.
know
Mhm.
the answer, but we do not know that the equilibria exists. So
Mhm.
um,
Perfect.
as I said, chiral magnets may be a good platform, but we have to check it out.
Good. And then for the second chapter, I had a question regarding. So you mentioned about the possibility to stabilize these lattices or like these patterns by polymerization, right?
Yes.
And my question is how stable these lattices are in time. So how stable this pattern is in order to frozen it.
Oh, okay. So they are very stable, very, very stable. So since they are constrained by by these droplet, now that's a very, very, very interesting question. So generally, whenever people go from the isotropic and cholesteric phase, they cool down the material, they will start to disappear. They will be annihilated by a saddle node bifurcation, and they will disappear. But what we do observe is that maybe for the constraint of the geometrical system, this remains, these cholesteric domains remains in as a Ablygasov cluster, sometimes for days. You can have 2-3 days of a Ablygasov cluster that is looking just like this one over here.
Mhm.
So the photopolymerization process, as I know, it should be very fast. I don't know how much time it can take. I don't think that more than an hour, since you have to photopolymerize it with UV light. I don't know the exposure that we have to put the chiral liquid crystal into the UV light. Nevertheless, the domain itself will be stable for a while. So at room temperature, that in our case is 18 degrees Celsius, we can expect 2 or 3 days of the same Ablygasov cluster.
Okay, perfect. So thank you very much. I mean, these were like the questions that remain after the previous ones. Really, really, really nice.
Thank you.
Thank you, Emiliano. Now we move to Professor Luis Foa. Normally he's not in Chile, but I don't know where Luis is. So Luis, could you ask your question?
Thank you, Marcel. Yeah, I'm now in Trieste for a conference and for a stay. So thanks again, Victor, for the talk and for the thesis. I have to really congratulate you for all the work you have done, and also Marcel as your advisor. It's really very nice work. I'm happy that that this took place. And I have just one kind of follow-up question. So in your study, one of the things that you demonstrate is this sort of universal topological transitions between disorder patterns that are driven by heating, the heating rate in these chiral nematic liquid crystals. You compare this with some how to say some well-known models and but I mean can you elaborate on how robust this universality that you have is with respect to experimental imperfections and whether you foresee practical applications that would be stemming out of this robustness for I don't know materials design sensing.
Okay, perfect. So In the case of the robustness of the universality of the transition, we expect that it should be very robust. The reason being is that this equation, the one that I'm showing right now, the non-variations with Hockenberg equation, is a prototype equation for pattern formation. We haven't worked on other platforms, well, but we can expect that if we see the equilibria, the transition between them should be continuous and should be explained through with this type of supercritical transition, which is the universality that we are exploring, right? So in the case of another materials, even if we are not able to, for example, work with chiral magnets because it's very expensive and it's very equipment heavy, it should be we should be able to explore, since we know that invagination patterns and branched patterns also exist in those systems. Now, regarding the experiments, the experimental applications, for example, that this type of transition can have, I think, well, there are two, maybe two. One of it not being an application directly, but an idea. So one of the things that I like to remark about this work is that, and the thing that I really liked is that there was one thing that I learned a lot of it, and finding, for example, these variables, these hidden variables that not a lot of people work with. Heating rate, if you look, for example, for the literature of liquid crystals, most of the time they don't even say it. They just say, okay, we go from this temperature to this one. So by changing the heating rate, we found out that there were these transitions. Okay, so maybe this type of motivation of process-dependent, for example, transitions of process-dependent variables, it can be applied to other systems. So now maybe not the heating rate, but another type of variables can be used in order that the process at which we are, for example, injecting energy to the system changes. And the second point that can also be useful for it is that the amounts of topological defects will emerge. So we can have a disordered these cholesteric patterns. So maybe I will go towards an image. So here at the left and the right, as I said before, the main difference is the amount of topological defects that we have in the system. Cholesteric patterns have not been worked as for example, as a device that in optics, for example, but it could. The reason being is since these locations are a topological defect, this can be also used, for example, to create disordered phase gratings, and it could be also which can also be a good idea to have. The reason why this could also be interesting is that this system remains fixed. This equilibrium is stable at this temperature. It moves very, very slowly. So maybe it's easier to photopolymerize. You can have, for example, a scattered amount of topological defects toward in the cell. And you can also find maybe topological optics applications from the topological properties. And it's now one of the things that we should try to work with is to see what could be the advantages of having a disordered pattern as, for example, optical vortex optical beam generator. That could be a good idea to follow up. Professor Fogg?
He's muted. You are muted, Luis.
Professor Fogg, I think you're muted.
Oh, yeah, but you are muted, Luis.
Okay. Hello?
Hello, can you hear me?
Yes,
Yeah.
Darren. Yes.
It's okay.
Yeah, it's sorry, it's the connection here is not as good. So things in Europe are not working as good. I think we have better connectivity in Chile. Sorry. So thanks a lot, Victor. It's I had some lag between your words, but it's I had the impression it's you have really still a lot to do with this. It's amazing. Congratulations again.
Thank you very much.
Thank you, Luis. So now we move to my position of advisor. So I change my role of chairman to advisor. So okay. So first of all, so I want to congratulate to Victor because for me was a very, very, very nice opportunity to work with him. When Victor tried to work with me, he was interested in metamaterials. But at the end, we study some self-organization that can be used as a metamaterial. So
Yes.
that was a good direction. But I'm very happy. I explain why I'm very proud for Victor, because Victor, when I arrived to my group, he was essentially more oriented to numerical analysis. But now for me, he's a real physicist in the sense that he do experiment, he did numerical analysis, also theoretical ones. So for me, this is a very, I'm very proud for that, because now for me, you're a physicist, not a numerical analysis man. Okay,
Yeah.
so thank you for that. With respect to your result, I'm very proud for the different result, but I want to ask you, my first question is related to the fact that, for instance, in the case of abricos of lattice, so the question, okay, are beautiful, wonderful, but are useful? What do you
Yeah.
think about that?
Well, we should expect that they should be useful. As I said, these chiral domains, they have been used as microlenses, face gratings, and other applications. But the reason why in the literature you don't really see that many applications is because the difficulty that you can have by trying to control this type of chiral domains. So the reason why the abricos of cluster experiment was very fulfilling, or it was a very nice experiment to do, is that by changing the confinement, we found a very efficient way to do it without having to have, for example, expensive optical equipment. And we can draw now these chiral domains in order to have, for example, our arrangement of the arrangement that we want. So we can have, for example, a metamaterial. Since each of these chiral domains has a topological charge, then we can, for example, a part of this exploration, we can, for example, I try to work with another groups, the ones that can work, for example, with optical telecommunications, in order to, for example, create channels, because in this case, each chiral domain can be a channel of light in order to transmit this information and create something similar to, for example, a bundle of optical fibers. But in this case, this bundle, instead of being just a lot of fibers one next to each other, it can be, in this case, the chiral domains. They can be separated. They are separated in micrometers, so they can be worked as a bundle.
Okay, now let me ask a question in the just opposite direction, because the defects are very important for the string theory also, for fundamental physics in principle.
Yes.
So my question is, what do you think about the possibility to apply this kind of abricos lattice to maybe string theory? Do you think there is some impact in this fundamental point of view of physics?
So, well, in the case of the abricos of lattice, maybe I'm not showing here right now, but these type of behaviors that we observe here are generalized into different type of platforms in the system. So there is a work, for example, that they also do an abricos of lattice equivalent, but in an holographic superconductor. So what they do is that they work, for example, in the most more cosmological approach to create these lattices, where they see, for example, similar behavior. So I think one of the things that I like the most about topology is its robustness and the way that we can observe it in different scales, in different platforms, in different systems overall. So in the case of, for example, maybe I don't really know very much about topological effects in string matter, but what I do know is that there are other systems, more complex systems, such as cosmology, that we are not able to have on a lab, but liquid crystal can maybe enable us to have this cosmology, even a cell that we can work with. So from this work, I think the idea that I like the most about working on these subjects is the idea of transmitting an idea, somehow a way that we can try to now explore different types of systems. And I think that this is a good way to start, for example, if we want to look or have an analogy, for example, to a cosmological most different type of system or more complex one that we cannot study so easy.
Okay, so my last question is related to the question of Pauline and also to Emiliano to this phenomenon that you show in this slide. So we claim that the heating rate change, driven this topologic transition.
Yes.
Okay, but normally I like to cook. So normally the people that cook, they know very well that when they cook with different cooking, I mean with different kitchens, so the results are different.
Yes.
So the only difference is the heating. So the question is why these people understand this very well and why this is difficult to explain to a physicist.
So yeah, it could be a good question. So yeah, I think sometimes one of the important things about physics is to try to connect it with the light that we have. So yeah, I think for example, a pot of rice is a good idea to start. So yeah, if you have the same pot of rice, but you go to different kitchens, you will have a different result. And at the end of the day, yeah, it's not the temperature. You can have the same temperature, but maybe the material is different, the way that you're heating up is different, and that will end up with a different result. So I think that everyone has had that problem. But for a more experimental, a more application point of view, I think the process dependency that can have, in this case, for example, the heating, are sometimes overlooked. So maybe, for example, in another system, such as chiral magnets, since I'm not very well familiarized with the variables that you work in chiral magnets, but sometimes this process dependency that is subjacent to any type of experimental setup can be used to try to find, for example, different equilibria, different transitions in our case. So I think the idea that I like the most about, for example, an experiment like this one is to motivate, for example, in the case process dependency transitions, that I think is an interesting idea to transmit.
Okay, thank you very much. I'd like to congratulate you again. So, okay, so now we move to the public. If there is any question of the public that have to write to ask question. Okay, it's not the case. So the committee have the last chance to ask question if there is any question of the committee. It is not the case. There is not question of any person of the committee. I mean, it's the last opportunity. Yeah. Okay. So if there is not question, so I ask to all the people to go out of the room in order to deliberate. I stop also to the YouTube. Now.